Okay, these were the questions I gave for review for the test tomorrow, which you haven't forgotten, I suppose. These here are not for the test tomorrow, so we'll do them later. Okay, the first was section 13, number 27. Okay, when a metal A is only slightly soluble in another metal B, we find that the curve of ln XA, where XA is the solubility, as a function of 1 over T, is pretty well represented by a straight line. Okay, explain this observation and what is the slope of that line equal to. Alright, so let me draw a diagram. Basically, we're going to have here, this is A and B, this is phase diagram temperature, and over here you have a, other way around. Over here you have a solution here, and this is the solubility XA. So this is your solution. Say liquid, solid, let's say liquid, say it's a liquid solution. And here you have liquid plus pure A, solid. So this is your liquidus line basically. The liquidus line and the solubility line are the same thing. That's a liquidus line, that's the line of the liquid phase composition in equilibrium with solid A. But if, of course, this line is way, way over towards B, then basically it's a solubility line. It's the same thing. Okay, so this is the liquidus line here. So along the liquidus line, the same equation applies as along a liquidus line. RT log activity on the liquidus equals minus the heat of fusion, Gibbs energy of fusion of A, which is minus the heat of fusion minus T delta S of fusion. That's then the equation of this line, assuming that it's in equilibrium with pure solid A. Okay, so here you take B and you add A, and when you reach this line, solid A precipitates. So this is the liquidus of A. So the activity is RT log XA plus the partial excess Gibbs energy of A, which is the partial heat of mixing of A minus TS excess A in the dilute solution here, equals the heat of fusion minus TS fusion of A. So rearranging this term then, they get log XA, so that's logarithm of XA, the solubility, is given by this expression. Now, when XA is approaching 0, we're talking about a very dilute solution here. When XA approaches 0, we apply Henry's law, which says that the activity coefficient, or delta HA and SXSA, are approximately constant. That's Henry's law. This is very dilute solution in A, so the partial heat and the excess entropy of A, or RT log gamma A, is approximately constant. And also we're assuming that the heat of fusion and the entropy of fusion are approximately constant. If all these terms in here are constant, then obviously this is just a linear ln XA is a constant over T plus another constant. Okay, or in other words, d log XA d1 over T is a straight line. Okay, so if you plot the liquidus as mole fraction versus temperature, you get a strong curve. You get a very strong curve. I mean, if you look at liquidus lines that come down to they come down very, very steeply here. But if you replot this in terms of log XA versus 1 over T, then you get almost a straight line. Not quite, of course, because the Henry's law isn't exact and the heats and entropy of fusion are not exact either, but it's pretty close to a straight line. And this is very important. I mean, you often have measurements of solubility are measured at higher temperatures where the solubility is higher and it's easier to measure. Okay, but how do you extrapolate this down to low temperature? I mean, if you have a very low temperature here, this is your eutectic temperature. This is the eutectic temperature. You'd like to know many systems, this eutectic temperature is it's just a half a degree lower, or almost indistinguishable from the melting point of pure B. Okay, so measuring solubilities down here would be extremely difficult. Measuring solubilities up here is relatively easier. Okay, now if you try to extrapolate the liquidus though, just an xt, it's a curve. How do you extrapolate a curve? So what you do is you replot these curves here as log x versus 1 over t, and now you can extrapolate linearly or a slight curvature, and you can get a pretty good estimation of what the solubility is at low temperature. Much more accurately than you could actually measure it down there. How do you actually measure solubility at low temperature? Well, at any temperature, the way to, the obvious thing is you take a liquid, you take your liquid solution, AB, and you saturate it with solid A. So here you have solid A, particles of solid A saturated the liquid, like think of it as water saturated with salt. Okay, but then you can take a sample of the liquid, you sample the liquid and measure its composition. But this can be, first of all, you got to measure the composition very accurately, but the other problem is that, unlike maybe, well, even with salt and water, but if you're doing this in a metal or a salt or something at high temperature, these particles don't stay down at the bottom nicely behaved. They can stir up in the liquid and you get little tiny particles of solid in the liquid. And when you take your sample of the liquid, you're always gathering up some of the solid. And then when you analyze it, you almost always analyze it as too much A. This is why if you look at people who've measured solubilities, small solubilities, by a technique like this, I find almost always, even though they take extreme precautions, you almost always find they overestimate the solubility. This, of course, is easier to measure up at higher temperature. So anyway, that's why it's a straight line. So log solubility versus 1 over T is the best way. Always, if you're going to extrapolate something, you try to make it linear. You can't extrapolate a curve. And if you did this, you could probably get a pretty good measurement of a pretty good estimation of the solubility at the eutectic temperature, even if this is 200 or 300 degrees lower, by using this sort of technique.
Question?
Another thing, if you're doing your phase diagram optimizations, if you take a solubility curve, and I mean a liquidus, but with just a few percent solubility, and they have measurements along here, just replot it this way. Take the experimental points and plot them as log XA versus 1 over T. And if it's not a straight line, or close to a straight line, then you know probably something's wrong with those measurements. And you'll often find that. You'll find people do these solubility measurements down to here, but you plot these points up and you find, they don't. All right. And I've seen people plot them up in papers like that and say, well, that's how the solubility goes. Well, that's nonsense. That would mean that suddenly the properties, thermodynamic properties, were constant and then suddenly decided for no good reason to change tremendously. So. All right, let's look at number 23. Okay, here's your iron-carbon phase diagram, atomic percent of carbon versus temperature. As you should know, this is the metastable phase diagram, because this is gamma phase, austenite, and this is gamma plus cementite, Fe3C. But this is because the actual equilibrium phase diagram, the line is just slightly to the left of this, and that's the equilibrium of iron gamma with carbon, with graphite. But since precipitation of graphite is very difficult, is kinetically hindered, unless you take certain ways of doing things, you end up with the gamma plus. Steel is not austenite plus carbon. Steel with high carbon will have Fe3C. Okay. This is strictly speaking, a metastable phase diagram where graphite does not precipitate. But it's the more practical diagram, at least in this region down here. So at 1100 degrees Celsius here, a mixture of CO and CO2 passes above a mixture of iron carbide and iron. In other words, you're somewhere in this region here. So you have a hypereutectoid steel containing austenite and Fe3C in this region. Okay, that's the iron is saturated, so the gamma iron is saturated with the Fe3C. Shouldn't say carbon, it should say Fe3C. At equilibrium, you measure PCO and PCO2, calculate the equilibrium coefficient of carbon in iron at 1100 degrees, and calculate the Gibbs energy of the formation of iron carbide. Okay, so trying to remember that diagram. first of all, I just put together those two equations to get this reaction here of CO2, CO, and carbon. Delta G naught is given. Delta G naught is minus RT log K. K is PCO squared, PCO divided by the activity of carbon, which is gamma times X. Now the mole fraction, so this is at equilibrium. This equilibrium with the gas phase will give you the activity of carbon. The mole fraction of carbon can be read from the diagram. So you go to the diagram at 1100 degrees and you go over, you're in a two-phase region, so the mole fraction of carbon in the gamma phase is given by the phase boundary, which I read off this diagram as 8.2%. So this 8.2 is the phase boundary here. The gamma phase composition saturated with cementite. So if we put that mole fraction of carbon into here, okay, we can then calculate the value of gamma, 8.5. Okay, so that's the Henry activity, because that's the activity coefficient of carbon in the gamma phase in equilibrium, on the phase boundary in equilibrium with cementite. Okay, now we take this reaction, iron plus carbon forms Fe3C. That's the equilibrium constant. So we're talking about the equilibrium now. We have iron carbide in equilibrium with carbon that's in the steel, in the gamma phase, and iron that's in the gamma phase. So iron is in the, iron and carbon are the solutions. K is the activity divided by this. The activity of iron carbide is 1 because it's pure iron carbide. We're going to assume the solution is Henrian, which at 8.2 atomic percent is probably not the most wonderful assumption, but it's not too bad. So if it's a solution, Henrian solution, the activity is gamma X, where gamma is constant. So we're assuming that gamma is independent of composition. The activity of iron is the mole fraction of iron, because if it's Henrian for the solute, it's Reynoldian for the solvent. So I put in 1 for the activity, 0.918, that's the mole fraction of iron on this phase boundary, gamma, X carbon, and then we can get the delta G naught of that reaction. Just showing you how phase diagrams and things are treated. Question 24, no, not 24, 26. And I just realized this morning that I actually don't have a, I didn't write down the answer to this question, so I'll have to write it out for you on the board here. So, a bath of lead at 750 Kelvin contains zinc as impurity. Calculate the minimum amount of zinc in the lead after distillation at a pressure of 0.01 torr. So the lead, you're trying to get the zinc out of the lead by distillation. So the lead, the solution's rich in lead at 750. You pump the thing down to 0.01 torr, and you lower the thing down to. Okay, so this is your heat. This is your boiling. This is your delta H of vaporization, and this is the boil. This is the T0, this is the standard boiling point. So the standard boiling point would be the temperature at which the partial pressure of zinc, which the partial pressure of zinc, or the vapor pressure of zinc, is 1 atmosphere. Okay, so this is the equilibrium boiling temperature. Standard boiling temperature of pure zinc. Okay, the system. Okay, then you also need the phase diagram of the lead zinc system. Where's the phase diagram of the lead zinc system? Is it not there? Oh, that's the answer. Oh, wait a minute.
It's on question 18.
Huh?
It's on question number 18.
It's question number, but where are the diagrams? What am I doing? What am I doing?
Just go to.
It's in. It's right behind the diagram.
says
is given in
motion 18.
See problem 18. Excuse me. All right, there's your lead zinc diagram. All right, and we're at 750 Kelvin, which is here, and we have a lead solution, so we're dealing with the solution. So, we're dealing with this. Yeah, we're dealing with the lead solution over here, lead-rich solution at 750, and we're going to be pumping it down to a very low composition of zinc, so we're somewhere over here. Okay, but from the phase diagram, you're going to have to get the... Sorry, I thought this was in there. So I have to write it down. Okay, we'll do the second part first. We got zinc, zinc liquid gives zinc gas. This is the equilibrium between the zinc and the liquid phase and the gas phase. And for that we have delta G0 is minus RT log K. Okay, and which is equal to the delta G standard for that reaction is the heat is delta H of the reaction minus T delta S of that reaction. All right, and the heat of the reaction is 114,200, which was given to you, minus T, and the delta S is 114,200 divided by the melting point. The entropy of fusion is the heat of fusion divided by the equilibrium melting point, which is known. The equilibrium melting point is 907 plus 273. Okay, so we're going to put in T equals 750 K. And I'm going to calculate the equilibrium constant at 750 K. And the equilibrium constant, if you substitute 750 K into that equation for the temperature, you end up with the equilibrium constant for that reaction. And the equilibrium constant is 0.0126, and that's equal then to, for that equilibrium constant, the partial pressure of zinc divided by the partial pressure of zinc in the gas divided by the activity of zinc in the liquid. Okay. This is your reaction, liquid and equilibrium of gas. The equilibrium constant is the partial pressure of zinc in the gas divided by the activity of zinc in the liquid. The equilibrium constant is obtained from the equilibrium boiling point and the heat of vaporization. Now you want the partial pressure of zinc to be 0.01 torr, so this is 0.01 divided by 760. Remember, partial pressures in equilibrium constants always have to be expressed in bar, or atmospheres. And the activity of zinc then is the mole fraction of zinc at equilibrium times gamma zinc in the liquid. So this is what you're trying to calculate. You're trying to calculate when this thing's at equilibrium. You're doing this at equilibrium with the gas phase with this partial pressure of zinc. What is the mole fraction of zinc? That'll be the minimum mole fraction you can get to. You're trying to take this liquid and distill it until you end up with the minimum mole fraction of zinc. Okay, so this is your... Why does it do that? It's just left. The whole thing is gone.
It's updating.
It is updating. Oh, I wish that she hadn't done that. Oh, what? Did it ask me?
Yeah, it was glowing like.
Oh, and I
orange thing was
didn't see it. Okay, so since I don't know how long it's going to take, I'll draw the bloody diagram on here. Here's was your two-phase region going from lead over to zinc. This was your two liquids. This was 750 K. Okay, 750 K, this is a dilute solution, and this is a very dilute solution over here. If you look at the phase diagram, this is about 99% zinc, and this is something else. So this liquid is in equilibrium with this liquid. So the activity of zinc here is equal to the activity of zinc here. Two phases in equilibrium have the same activity, and the activity of lead here is equal to the activity of lead here. So I can write the activity of zinc, let's call that liquid 1, and we'll call that liquid 2. The activity of zinc in liquid 1 equals the activity of zinc in liquid 2 when the two are in equilibrium. That is, the activity of zinc here equals the activity of zinc here. The activity of zinc in liquid 1, this point here, is a mole fraction of approximately 0.08. If you read it, this is read off the phase diagram. Okay, so I have 0.08 times gamma zinc in liquid 1 equals the activity of zinc in liquid 2, and this point here is about 0.99 mole fraction of zinc, so this is an Ariolean solution. Okay, so it's 0.99. Okay, so the activity coefficient of zinc here can be calculated from this two-phase equilibrium. Okay, and so we get gamma of zinc in liquid 1 equals 0.4 from the phase diagram. Okay, so now we assume that, I'm assuming that at 8%, I have to make an assumption, I'm assuming that at 8% the solution here is Henrian, which is not perfect, but it's not too bad. In other words, I'm assuming that the gamma, this is the gamma zinc at that point. In this, there's no assumption really. This is the gamma zinc at that point. But if I assume that applied this, but I mean the actual liquid after we pump it down is going to be way over here, but we're assuming that the gamma remains constant. So I simply take now that I've got my gamma zinc from the phase diagram, I put the gamma zinc into here, into this equation to be 12.4, and I can calculate the mole fraction of zinc at equilibrium is 8.4 times 10 to the minus 4. Okay, so next time it does that, somebody say, "Please don't yell at me to tell me to stop. Tell it to stop." Password. Any questions there? No. Okay. These questions are kind of designed to show you what information you can get from phase diagrams, and that phase diagram, because it's very, very dilute on this side. It's almost the solution down here. This is Ariolean is a very good assumption, and that permits you to calculate the activity coefficient of zinc along this sort of line, phase boundary. If this is also dilute, you can even assume it's Henrian. Okay, next then I said that I wanted to go to the previous exam. This was the control number 1 in 2005, and to do questions 1 to 4. I don't know if you know this, but yesterday I put the answers for that up on the website too. I guess I didn't mention. Did anybody see them? I should have written that to you, but they are actually there. It was number 30A. Anyway, so this was the old exams, PDF, number 30. What happened to 30A? Oh shit, I didn't put it on. Oh. Put it on here. Right here. Put it. There. Okay, this 2005, control 1, questions 1 to 4. And it would seem that I forgot to put it onto my thing here. So, you've been here with me for about 3 minutes, so I'll just copy it on through the numbers. Need a break. Darn. It is where it's supposed to go. Let's see. Come on. Won't work. Don't understand that. All right, there are your answers for it. Okay, let's do the 4 questions. As I said, this was a quiz from 2005, which was fairly difficult, although this particular question wasn't. So the nitrogen content of liquid iron in equilibrium at 1600 degrees with a gas phase in which the pressure of nitrogen is 1 bar is 0.045 weight percent. Calculate the nitrogen content in equilibrium with a gas phase in which the pressure is 10 bars, assuming it dissolves as monatomic nitrogen. State your suppositions. So we go to the answer, which is, all right, you have an equilibrium, between nitrogen gas and nitrogen dissolved in the steel. And it's very important that it dissolves monotomically, because then you have 2N. If it dissolved as N2 molecules, then you would have N2 equals N2 dissolved, and this makes a big difference. So the equilibrium constant is the activity of nitrogen squared, Pn2. Okay, so it's the mole fraction, the activity of nitrogen is the mole fraction of nitrogen times gamma nitrogen times Pn2. I don't want my goddamn free update on any of this stuff. I gotta get that. Alright, so it's the mole fraction nitrogen times gamma nitrogen squared times Pn2. Assuming a Henrian solution, so gamma nitrogen is constant. Also in a dilute solution, the weight percent is approximately a linear function of the mole percent. If you put in something that's almost pure iron, then the weight percent is almost a constant to the mole percent, right? So therefore, weight percent nitrogen squared over Pn2 is approximately constant. So the gamma is constant. the C, so simply, I don't have to know what C is or what gamma is. All I know is that weight percent nitrogen squared over PN2 is approximately constant. That's called Sievert's law. Sievert's law is that the weight percent or the mole percent, doesn't matter. In a dilute solution, the weight percent or the mole percent varies as squared, varies as PN2. Or we could do it the other way. We could say that weight percent over PN2 to the 1/2 equals a constant. So the weight percent varies as the partial pressure to the 1/2 if the diatomic gas dissolves as a monatomic gas. If the diatomic gas dissolved actually as N2 molecules, then there wouldn't be an half here. And the weight percent would vary as PN2. Okay, the weight percent is a constant times PN2 to the 1/2. If the diatomic gas dissolves as a monatomic, okay, and so you get the 1/2 variation here, and so on. So this is very important. This can make a huge difference in the how you extrapolate the thing. Okay, so you've got to extrapolate it this way, weight percent squared. So the weight percent at 1 atmosphere is 0.045, so you can calculate the weight percent at 10 atmospheres. Okay, is 0.045 times root 10. Okay, if it dissolved as diatomic, then it would be 0.045 times 10, which would be quite a bit bigger. Okay, and so on. So it's basically Henry's law and the fact that the equilibrium constant reflects the molecular. So it's very important to know how. So a monatomic, if you dissolve argon in steel, the solubility varies as the partial pressure of argon, because argon is a monatomic gas. So if you dissolve argon in steel, the solubility varies as pressure of argon. If you dissolve nitrogen, it varies as PN2 to the 1/2. Same thing for oxygen. If you dissolve oxygen in water, the oxygen in steel, molten metals, the oxygen dissolves as O monatomic atoms. If you dissolve, so it varies as PO2 to the 1/2, or if you dissolve oxygen in water, it dissolves as oxygen molecules, O2. So in water, the solubility of oxygen varies as PO2. So that's how you see this one. Okay, question 2. Phase diagram is sketched in figure 1. Okay, well, you've seen these diagrams. Talked about this before. There you have a diagram. This is, you've seen this. This is PC, equilibrium partial pressure of chlorine versus the silver-copper ratio at a constant temperature. So this is an isothermal constant temperature diagram, equilibrium chlorine pressure versus the silver-copper ratio. So you have here a metal solution rich in silver. You have here a metal solution rich in copper, and up here you have a liquid solution of the two materials. And we show diagrams like this we're showing in the chapter. Given various information in the thing, I'd like you to calculate the compositions at points A, B, and C, as well as the equilibrium chlorine pressure for this invariant point. This is the invariant partial pressure, in which you can have the liquid as an equilibrium with both solid alloy phases at one time. That's the only partial pressure of chlorine in which all three phases can be at equilibrium. Okay, so question 2 then contained some data. Okay, the Henryan, the silver solution, the silver-rich solution is a Henryan solution with RT log gamma Henry of copper is that, so that's a constant activity coefficient of copper. And the copper solid is a Henryan solution where RT log of the solute is that. The liquid solution is ideal, and I give you the Gibbs energy change for the reactions between pure silver and chlorine and pure copper and chlorine. Okay, the solid solutions are Henryan, so Rayleigh law is obeyed for the solvents. So we're going to the silver. This is the solution, the solid solution that's rich in silver. RT log gamma copper is that, so gamma copper, this is a constant temperature diagram, so we can calculate the activity coefficient of copper, which we assume is constant because it's Henryan. So the activity of copper is gamma times the mole fraction or this is the mole fraction of copper in that liquid solution. I call that x-axis, I call it psi because it can apply to both the metal, but it's the mole fraction of copper in the solution. And the activity of silver at point A. And the activity of silver is 1 minus XA, 1 minus XIA because it's relative for the solvent. XIA is the composition of the silver-rich end of the 350. And we do the same thing at the other end. At the copper-rich solution, this was point C, I guess, at the right-hand side of that invariant line. And the activity of silver is that, and the activity of copper is that. So these two solutions are in equilibrium. All three solutions are in equilibrium along that line, the two metals and the chloride, but the two alloys are in equilibrium. Therefore, the activities of silver and copper are equal in the two solutions. So I can set the activity of silver equal, the activity of copper equal, and solve the two equations, and that's exactly what I did with the lead-zinc system. A minute ago in the lead-zinc system, I had two phases in equilibrium. I set the activity of zinc at one end equal to. Okay, so here I have the two equations and I solve. So I have the composition at point A at one end, and I have the composition at point C at the other. So the silver-rich solution contains 10% copper, and the copper solution contains 3.2% silver. Now you got to calculate the composition of the silver-copper chloride solution in the middle. Okay, so I took the first equilibrium, silver plus chlorine and silver chloride, L to G naught minus RT log K. K is the activity of silver chloride, etc., etc. Okay, so the activity of silver chloride is equal to the mole fraction at point B, because that's an ideal liquid, and it's in equilibrium with silver. Activity of silver at point A, which is 1 minus Ia, which you've already calculated, times the pressure of chlorine to the 1/2. This should be P prime chlorine. And we substitute this in here. And the same thing for the copper chloride. So we get the activity of copper chloride. The activity of copper chloride in the liquid is ideal, so it's 1 minus the composition at point B times the activity of copper times PCl2 to the 1/2. So we have two equations here with two unknowns, Xi B and pressure of Cl2 can equate. So we have this equation with Xi B and PCl2, and this equation with Xi B and PCl2. So we solve the two equations to get the composition at point B and the partial pressure of chlorine at equilibrium. That's the point. If you were to take, say, this equation here for silver, chlorine, and silver chloride in equilibrium, if we were to put the activity of silver chloride as 1, and the activity of silver to be 1, and then put 1 here and 1 here, then this partial pressure of chlorine would be the partial pressure of chlorine where silver and silver chloride pure are in equilibrium. In other words, they would be the that would give me the partial pressure of chlorine up here. And in the second equation, I could get the partial pressure of chlorine here. Okay. Question?
How can we say that it's eta B for the activity of silver chloride?
I said it was an ideal solution. It's in the...
And why it's not eta... Okay.
It's just given that it's ideal solution. It's not quite, but it's pretty close. So don't say no, say. Three. Phase diagram of a system AB is sketched in figure 2. The compound A2B is stoichiometric. Solubility of B and A has been measured as 0.02 at 1,000 and 0.03 at 700 as shown in the figure. The melting point of pure A is 500 as in the figure. The enthalpy of fusion of pure A is given. And finally, the Gibbs energy of formation of the compound has been measured independently. That's the Gibbs energy of formation of the compound from the pure solid A and B. So the Gibbs energy of formation for that formation reaction from the pure solids is given by that equation. In the dilute region, we're assuming the liquid is Henrian. Calculate the activity coefficient relative to pure solid B as standard state at those two temperatures, and calculate the eutectic temperature and liquid composition. Okay, so let's go to the picture. I gone too far this time. There we go. Okay, so once again you have solubility here has been measured as 0.02, so this is very dilute. Solubility here is 0.003. Melting point here is 500. We're given the Gibbs energy information of the stoichiometric compound. I asked you to calculate the gamma in the liquid phase to calculate the activity coefficient of B at this point and at this point relative to pure B. And I also want you to calculate the coordinates of the eutectic point, the mole fraction of B at the eutectic and the temperature of the eutectic. All right. So, well, we have this reaction here. This reaction was given, solid, solid, solid. This is given, and this is the Gibbs energy information from the pure solids. But I want the Gibbs energy information from liquid A because, well, we'll see. I want it from liquid A. So I have to convert this equation to this formation equation from liquid A and solid B. So I have this equation. Solid A gives you liquid A. That's the Gibbs energy of fusion, which is 5,000 minus 10T. Because the entropy of fusion is 5,000 over T of fusion, and we're assuming H and S are independent of temperature. So the Gibbs energy of fusion is the heat of fusion minus 5,000 over 500. Okay, then I take this reaction here. This reaction minus this reaction gives me this reaction. So the Gibbs energy of this reaction is this one, or minus 2 times this one. There's 2 in there. So this is the Gibbs energy this is the Gibbs energy here of formation of A2B solid from liquid A and the solid B. And so this reaction then, the delta G naught, I calculated at 3 different temperatures, 1,700 and 500. And this delta G naught is minus RT log K for this reaction. Okay, so at 1,000 degrees, you've got minus 17,000 is minus RT log K. K then is 7.53 is the ratio of the activity of this with respect to the solid standard state, the activity of A with respect to the liquid standard state squared, and the activity of B with respect to the solid standard state. Okay. Now, this is important when you say delta G, this equation, delta G standard is minus RT log K. The equilibrium constant then is given with respect to the same standard states as are used in the delta G0. That's the whole point of this. This is solid A, solid B, and liquid A, solid A2B, solid B, and liquid A. So in the equilibrium constant, then if I take the delta G0 standard of that reaction, those are the standard states. So it's the ratio of the activities with respect to these standard states. So it's the activity of A2B with respect to solid A2B, the activity of A with respect to pure liquid A, the activity of B with respect to solid B. So the activity of A2B, this is your liquidus point, so these 3 phases are in equilibrium. The activity of A2B solid is 1, it's pure A2B. The reason I make this liquid is because at saturation, the activity of A is, assuming it's pretty close to a Henrian Rayleighian solution, A is the solvent. Okay, so it's very, very rich in A. So the activity of A is mole fraction of A. But that's with respect to the liquid standard state. That's why I had to make this conversion. Okay. If we go to the phase diagram here, we're talking about this point here. I think we'll move. We go to this point here, and this is the liquid A up here. So the activity of, this is rich in A, so the activity of liquid A is 0.98. With respect to the liquid standard state, not with respect to solid A. So therefore, I can use the measurement from the phase diagram that this is 0.98. Okay, but I have to have the Gibbs energy with respect to the liquid standard state if I'm going to do that. All right, so I put in here then 1 minus XB is is 1 minus, so it's 0.98 squared. XB times gamma B. XB is 0.02, and that's the activity coefficient of B. Okay, in the liquid, but with respect to the solid standard state. Is that perfect? I'm talking about, this is the activity coefficient in the liquid, but with respect to the solid standard state. So the activity coefficient of B is 6.74. And at 700 degrees, I can calculate the activity coefficient of B at 700 degrees in exactly the same manner. And now we do it back the way we did in question 27. Okay, basically we have the solubility curve. What we've really done here then, you see, is we have the solubility curve at 2 different temperatures. And now we're extrapolating that solubility curve down to a low temperature, okay, using the fact that log solubility varies as 1 over T. Okay, so the measurements have been made up here at high temperature. We're extrapolating that down to around 500 K. Okay, but you can't, the way to do that is, as I say, you've got to do it thermodynamically, log K, log solubility versus 1 over T. Or, which is simply the same thing then, as I'm saying RT log gamma Henry B. Satisfy yourself that I'm saying the same thing. RT log gamma B is A minus BT. Okay, so I can calculate RT log gamma B at 1,000 degrees and at 700 degrees is given. Okay, so I can solve to get the linear expression here. So now I have RT log gamma B now as a function of T, assuming that A and B are the partial heat and entropy of mixing of component B. RT log gamma B, this is G excess of B. If you want to take that equation, this is RT log gamma Henry of B, which is G excess of B, which is the partial heat of mixing of B minus the partial excess entropy of B, which we're assuming to be independent of temperature, which is the same assumptions as I made up here in 27. Alright, so this permits us then to calculate so at 500 degrees Kelvin then, I can then, so from these two values at 1,000 and 700, I can get the linear, I can get the A and B, which are the enthalpy and entropy, the H and S partial. And I extrapolate that thing down to get gamma at 500 degrees. So at 500 degrees, the Henry activity coefficient is 2.323. What is the equilibrium constant? Well, equilibrium constant for this reaction. I'm doing the equilibrium constant for that reaction again. I can then get the equilibrium constant at 500 degrees is 1, same thing, it's 1 over the mole fraction, so I can calculate the composition at the eutectic. Okay, so as I said, this you could never measure 0.00025, but this gives me the mole fraction of B at 500 degrees. So what is the eutectic temperature? Well, now I'm using the liquidus, the A liquidus, which is really, can't even see it, but the A liquidus is this little line along here. A little line along here, RT log activity of A is the heat of fusion, 1 minus T over T fusion. I've now calculated at 500 degrees Kelvin, I've calculated this mole fraction of B is 0.00025. Now I want to calculate the temperature. So I calculate the temperature by simply saying along the liquidus, RT log activity is minus the Gibbs energy of fusion. R eutectic log activity of A is the mole fraction of A at the eutectic point, which is almost 1, is delta H minus T. Okay, so I can calculate that. So the eutectic temperature is 499.9 Kelvin, almost exactly 500, with a very low solubility. That was not an easy question. I don't know if anybody got that right. Always like to give one question that challenges you. Any questions or not?
Yeah, here we are equating your activity coefficient of at 500 Kelvin to you at utility temperature. become
Well,
low.
500 degrees Kelvin is clearly the eutectic temperature. I know the eutectic temperature is going to be really, really close to 500. Yeah, I mean, strictly speaking, if the eutectic temperature wasn't 500, then I'd have to kind of do an iterative process.
But the activity will be different at both different temperatures.
Well, yeah, because of this.
Yeah, and
Well, because of this equation, the RT
Yeah.
log gamma. So I've got the Henry activity coefficient. I know the Henry activity coefficient at 1,000. It's 6.74, and I know it at 700. It's 4.269. So that permits me to make this linear equation, and I extrapolate this same equation down linearly and solve it at 500 degrees to get the activity coefficient of 500. Then the equilibrium constant then is the activity divided by that. Putting this number in here. No, the gamma Henry is not, the gamma is not constant with temperature. You sometimes see this too. I mean, okay, it's the other way of saying, but the activity coefficient, you'll sometimes see, this is wrong, but I've seen this done, is, say you got one temperature, here you got the activity called gamma Henry, you get gamma B. And they say, okay, well, let's assume gamma B is independent of temperature. Well, no, it's not. Gamma B, Henry laws is gamma B is independent of composition at a given temperature, but it's not independent of temperature. It's given by an equation like this. RT log gamma B is H minus TSXS. So to a first approximation, RT log gamma is linear with temperature. Okay, or log of the Henry activity coefficient is delta H over RT minus SXS. Okay, so log gamma varies as 1 over T. Okay, so it's not constant with temperature. Now, suppose if you have it at 2 temperatures, here it's been measured at 2 temperatures, so that permits me to get delta H and SXS, which I assume are independent. That's a fairly good assumption that they're independent of temperature. It's not perfect, of course, but I mean, that's pretty close. As I say, usually we don't assume that, we assume the excess heat capacity is 0, so the heat and excess entropy are independent of temperature. So you get so if you have 2 points, if you've measured log gamma B at 2 different temperatures, that permits you then to do a linear extrapolation. Basically, I'm just plotting log gamma Henry of B versus 1 over T, and I've got 2 points, so I'm just extrapolating that linearly to a third point. If you only have it at 1 temperature, if I only had 1 measurement at 700, how would I get it at 500? Even then, I wouldn't assume it was the constant. I would simply set this to be 0, and I would do it that way. This is usually smaller than that. Okay, so I mean, if you have 2 points or more, then you do your linear extrapolation. If you have only 1 point, then do it this way. But don't ever assume that gamma is independent of temperature. Oh, actually, well, okay. Assuming gamma is independent of temperature would be equivalent to assuming the excess heat was 0 and the excess entropy wasn't, which is not what you observe.
In the first eutectic point, the second liquid acid gives the activity of A to B.
Yeah, but you don't need that. Well, you don't have
Yeah,
any.
I mean that, but I'm asking to make sure for myself. And for the second one, the first liquid gives the activity of A to B, and the second one A to B.
This liquidus gives you the activity of A,
Yes.
and this liquidus gives you the activity of A to B.
Yes, and can we calculate the activity of B along this liquidus? No. Yes.
Well, you can calculate the activity of, well, yeah, we have calculated the activity of B along that liquidus in the first
Yeah,
part of the
that's-
question. We calculated the activity of B. We just did it. That was part A of the question.
So it doesn't matter that
No. I calculated the activity, well, in the first part of the question, those activity coefficients I calculated are the activity of B solid at those 2 points.
yeah, I mean the RTLN AB in liquid minus RTLN A being solid equal to minus delta G of delta G fusion of B is also applying in this liquid.
No, no, this is the liquidus of A to B. So along this liquidus, RT log activity of A to B equals minus the heat of fusion of A to B, 1 minus T over T fusion of A to B. Or T fusion of A to B is this temperature here. This is the heat of fusion of the compound, and that's the activity of A to B in the liquid Okay, this is the liquid that's in equilibrium with this solid. Okay, RT log activity of B equals the heat of fusion of B, 1 minus T over T fusion of B. That applies along this line. So that line, this line here would give you the activity of A2B, but you'd have to know the heat of fusion of A2B and the temperature of fusion of A2B. Which we don't have, but he had additional information. He had the heat of formation of A2B, which permitted us to do what I did and get the activity of B along that line. Now, if you wanted to, we have the activity of B with respect to the solid along that line. We calculated it. The activity of A along that line is equal to the mole fraction, because it's a rail-tune solution. The activity of A2B then is now let me not do that. That's going to confuse you. Forget that. Okay. All right, it's okay. Yes.
Yeah.
If the temperature is somewhat below than 500 Kelvin, it's not very good. How can we calculate that?
Oh, then you'd have to do it. You'd have to do it iteratively. I mean, I guessed that it was 500. So I calculated the activity coefficient of B at 500, and then using this liquidus, I calculated the liquidus temperature, which is 499.9. Let's say I guessed it to be 500, and then I calculated this line, and I find the temperature to be 480. Okay, we'll then do a second step. Go back to the first step, calculate the activity coefficient at 480, and then use this line to get the eutectic temperature. And you'll find 475, then do it again at 475. Do a couple of iterations. But I mean, 10 degrees is not going to change significantly. If you found it to be, 400 degrees, then do a second iteration. Recalculate it at 400, calculate the eutectic composition at 400, then calculate the temperature, and then do one more iteration. 4. Silver potassium chloride diagram. The solubility is a simple eutectic solution. Eutectic temperature is 306. The melting points are given on the diagram. The enthalpies of fusion are given here, 13,200. Assume the liquid is a strictly regular solution. By strictly regular, I mean SXS is 0, so this is all heat. Or A is independent of T, composition and temperature. Okay, calculate the value of the constant A as well as the composition of the liquid at the eutectic temperature. So you've got a phase diagram like that, and you want to calculate the eutectic temperature and the eutectic composition. The liquid is a regular solution, and you've got the heats of fusion here. And as usual, we will make the simplifying assumption that the heats of fusion are independent of T. So you have two liquidus lines. You have the silver chloride liquidus. This is the liquid in equilibrium with solid silver chloride. RT log activity is minus the Gibbs energy of fusion. You don't have this is the second term. Minus RT log of this in the solid is 0 because the solid is pure silver chloride. RT log X plus GXS is minus 13. Again, here I'm assuming that the heat of fusion is independent of T. And the excess Gibbs energy of silver chloride is since the integral GXS is AX1, X2, GXS of 1 is AX2 squared. Okay, you gotta memorize that. Okay, if GXS is AX1, X2, then GXS of 1 is AX2 squared, and GXS of 2 is AX1 squared. Okay, so that's the equation you get from the silver chloride liquidus. From the potassium chloride liquidus, we get the same expression, similar expression. And the two liquidus curves meet at the eutectic temperature. So at the eutectic temperature, T, if I put T eutectic into here, then the two curves give you the same compositions. Okay, so I just simply have two curves intersecting. Okay, so the first equation is RT, and the temperature of the eutectic then is 579. So if I put the eutectic temperature in here, then these are the eutectic composition. This is the eutectic composition, X eutectic, at 579. And I do the same thing in here for X eutectic at 579. So now I have two equations with the two unknowns, X eutectic and A, and two equations with two unknowns, which I can solve by iterative process. So these are the two equations here. Solve it iteratively and you can get the composition and the regular solution parameter. Which is what, of course, you'd be doing if you were to put those two, if you put the eutectic point into your optimizer, or if you were to do this with the optimizer routine, or you to do this by hand. This is basically optimization. Assume the liquid is a regular solution from the eutectic point. All you would need then is the eutectic point. If you assume the liquid is a regular solution, and you had only the eutectic temperature, and you assume the liquid was a regular solution, and further, oh well, okay, if you know that there's no solid solubility, that the diagrams are simply eutectic, you know the eutectic temperature, okay, assume the liquid's a regular solution, you have all the information necessary to get the eutectic composition and the regular solution parameter. You only need the one temperature. If you're really sure of those things, you don't need an awful lot more than just eutectic temperature would permit you to get these two things. If you know it's a regular solution, or pretty close to a regular solution. So I mean, if you have a phase diagram, you don't know much about it, but you know, you're pretty certain it's a eutectic mixture, and you're pretty sure there's very little solid solubility, and all you've measured is the eutectic temperature, which is easy to do on a cooling curve. If this is not too far from ideality, you can probably calculate the eutectic composition and the regular solution parameter with reasonable accuracy as a rough estimation, just from the one datum of the eutectic temperature. Now, of course, if it's not a regular solution, or it's far from regular, then that's not going to work, or if there's lots of solid solubility. You gotta look here at the minimum number of variables required, the minimum number of variables of adjustable parameters that you're putting into your equation, and the things you're trying to calculate are the number of equations you have. Again, sometimes this is, you know, sometimes it isn't obvious what when you're doing the optimization, whether you have a fully, you know, how many equations do you have, how many variables do you have? Do you have something that you can completely solve, or what? In this case, you have two equations and you have two variables, so you're getting an exact solution. If you have two equations and three variables, you're not getting an exact solution. Okay, you're getting, well, you're getting an average sort of thing. If you go the other way and you have three equations and two variables, then your system is overdetermined. You can't. Okay, so think about how many equations you're getting. Again, that's why we're doing these things by hand. Okay, so that was the things I gave for review. Okay, so what I intend to do now is go on to taking up the questions about the Gibbs-Duhem equation, which is not for the exam tomorrow. This is for the material, and then just continue on with the lectures. Unless you have some other questions you'd like to ask about review problems, questions you've seen, problems you've seen, any questions you have about the material up to where the exam is going to be about. Okay.
Chapter 2, problem 11.
2:11.
About, can you explain what reaction steps did you consider?
2:11. Right here. Oh, I'm in the wrong. Anybody want to look at these things again? The old exams? Not here. You get annoying. Oh, yeah. That's a complicated one. Iron silicon alloy with 5 weight percent silicon is used in transformers. To prepare the alloy, we don't use those anymore, we use iron neodymium now. Iron silicon was used because it's good ferroelectric with a very high, what do you call it, magnetic susceptibility. Now we use rare earths, which we buy from the Chinese, and put ourselves completely indebted to the Chinese. Anyway, another story. We've closed down all the rare earth plants in the rest of the world. If the Chinese decided to stop selling us neodymium, it would be screwed. Anyway, to prepare the alloy, we add ferrosilicium, Fe 1/2, silicon 1/2. Why don't you add pure silicon? Because it's ferrosilicon's a lot cheaper. Okay, to make pure silicon is difficult. To make ferrosilicon is not so hard. You get a great big bath of iron to reduce the silicon it goes in there. You add the ferrosilicon solid at 25 degrees, and so you have your bath of liquid at 1600 degrees, your bath of iron at 1600 degrees. You add in your iron's ferrosilicon at 25 degrees. You heat up the ferrosilicon. This cools down the iron. What is the final temperature of the bath if the process is adiabatic? And this is the partial heat of mixing of silicon. This is the heat of mixing of the liquid. This is the integral heat of mixing of pure liquid iron and pure liquid silicon. Okay, this is the heat of mixing at 1873 of pure iron and pure liquid silicon. This is the heat required to heat 1 mole of ferrosilicon from, This is wrong. This should be 298 here. Okay, there's your problem. I'm sorry. This is wrong. This is the heat. This is the heat required to heat the ferrosilicon from 298 Kelvin in the solid to 1873 Kelvin in the liquid. So this is obviously this is wrong. Is that your was that the problem?
Yeah, it's actually okay, but
okay, so there's an error. This should be 298 K. So this is the heat. If you take 1 mole of Fe 0.5 Si 0.5, meaning half a mole of iron and half a mole of silicon, solid, at 298, and you heat it to 1873, this is the heat required. And that includes everything. That's to heat up the solid, to melt it, to form the liquid. Okay. This is the heat capacity of liquid iron, the heat capacity of liquid silicon, and to get the heat capacity of the alloy, we're using Knopp's rule, which says that the delta Cp is 0, or that the heat capacity of the alloy is simply a linear function of the heat capacities of the pure materials.
actually, in the solution you gave us, everything is clear except step 3.
This is a difficult question. I don't think I will give you something quite that complicated on it, so. But it's a neat question. What is rather interesting in this question is if you, well, I mean, it's like if you take, well, the question 2, I think you take liquid copper at whatever high temperature and you add solid copper at 25, it clearly cools down the material. So if I take liquid iron and I add the iron silicide at iron ferrosilicium or ferrosilicon, 25 degrees Celsius, is going to cool it down. But at the same time, you have a negative heat of mixing. The delta H is very negative. Okay, so when the silicon goes into the solution, it's an exothermic reaction. And in other words, there's very, very strong bonds between iron and silicon. And that then gives off heat, which tends to heat the thing up again. Okay, so it doesn't cool it down nearly as much as if there weren't this negative heat of mixing. In fact, if you were to add pure silicon, not ferrosilicon, but if you take you can redo the calculation. If you take a bath of iron at 1600 degrees and add pure silicon to it, the final temperature is higher than 1600 degrees. In other words, all the heat, it takes up the, put the heat the solid silicon from 25, melt it, and go into the liquid. It lowers the temperature, but the heat of mixing is so negative that it more than counteracts it, and the final temperature will be higher than you started with. So that shows that these heats of mixing are by no means trivial. I mean, the heat of mixing of iron and silicon in these things is greater than all the heat required to heat the thing from 25 degrees to 1600 degrees, so it's nothing that you can ignore. Anyway, I took 5 grams of silicon, I convert this into mole fractions, that's fine. This is the final composition I want. I want the final composition to be 5%. I say but the final solution, the final steel has to be this composition, so this is the final composition in mole percent. Okay, so the first step is I take the ferrosilicon at 25 degrees Celsius, expressed in terms of that much ferrosilicon, and I add it to that much iron at 1600 degrees. So this is the initial state. My initial state is that many moles of iron at 1600 and that many moles of ferrosilicon at 25. Then these are hypothetical steps. I want to get to the final thing, which is 1 mole of solution at T. But I've got to do this in stages that I can calculate, for which I have data. So my first step is simply to heat the ferrosilicon up. And that is your 19 kilocalories, which, sorry, the question was wrong. So this is your, simply to heat the ferrosilicon, so that's positive. Then I want to mix the ferrosilicon with the iron. But the heat of mixing, I gave you the table I gave you as the heat of mixing. The heat of mixing is mixing pure iron and pure silicon. Here I have ferrosilicon already mixed. Okay, so I don't have a table that tells you already mixed plus iron, so I have the first step, I've got to unmix it. Okay, so what I do is I take this ferrosilicon liquid, which is 50%, 50 mole percent silicon and iron, and I unmix it. Okay, which then gives me 0.0948 moles of silicon, and this iron then goes on together with this iron. So this is an unmixing. So this is minus the heat of mixing at that composition. So I take this composition of 50-50 and I unmix it, multiplied by the total number of moles. Now, okay, so this is minus this delta H2, so delta H1, okay, so anyway, let's go back here. Delta H1 is to heat up the ferrosilicon, so that's the total number of moles times your 19,000. Step 2 is unmixing, so I'm unmixing it at 50 mole percent, so this is the heat of mixing at 50 mole percent. This is a 50 mole percent solution, so I'm taking this solution here, which is a 50-50 mixture. So its heat of mixing, to unmix it, is minus the heat of mixing at 0.5, which is 8930 from the table, multiplied by the total number of moles over here. So that's step 2, to unmix the iron silicon. So now I have pure silicon and pure iron, and now I mix them. Okay, so now I just simply take the heat of mixing at 0.0948, which is minus 2650 per mole, but I think the table was in moles. Okay, I'm dealing with 1 mole total. I put the whole thing on 1 total mole because that's, no, I didn't put it on 1 total. Oh yes, I did. This is the mole fraction. It's 1 mole. I put it into, I did everything in terms of, these add up to 1. Did it on a molar basis. So delta H3 is simply the heat of mixing at 0.0948 per mole. Delta H4 then is the delta H4 then. So delta H3 is taking the pure materials at 1600 and mixing them to form 1 mole of solution at 1600 at that composition. Number 4 then is to cool the solution down from 1873 to T, which is the number of moles of silicon times Cp of silicon plus the number of moles of iron times Cp of iron, assuming that the delta Cp is 0. And then equating the whole thing to 0, because it's adiabatic, I end up with the final. So it is lower than 1600, but the reason is I didn't add pure silicon, I added ferrosilicon, so the iron was heating up. But if you do it with just pure silicon, you'll end up actually, I think, with something like 1630 or something. So it more than counteracts. So if you take your bath of steel, you throw in pure silicon, you heat the thing. It's quite amazing. Any other questions from the devoir or old quizzes or anything you'd like to... Okay, well, let's take a little break then, and then after the break I'll do this question, series 12, numbers 5 and 7. course, maybe. Oh, okay. Do this. Oh, that's not what I want to do. That is not what I want to do.
This one is stopped.
Sorry?
This is already updated, so.
It stopped when it updated. All right, well, we've
anyway,
lost
I was
that.
recording, so probably it's enough.
Okay.